Welcome back to the next and last video of the chapter, everybody. Today we're going to be looking at ordinariness and flatness as deformation conditions. So the setup is we're still laying out some of the main deformation conditions needed to prove semi-stable modularity. In this video, we'll look at residual representations, rho bar, from gk sub lambda. So k sub lambda is some field completed at some prime lambda to GL2 of little k, where k sub lambda is a local field, and we'll suppose now that L, the residual characteristic of k sub lambda, equals P, which is the characteristic of the finite field K. We'll denote again by I the inertia subgroup of G sub K sub lambda. Okay, so the usual setup, we'll say that such a rho bar is ordinary and ramified. It's equivalent to a representation of the following sort of upper triangular form. G maps to chi1 bar of G star 0 chi2 bar of G, where chi1 bar is an unramified character and chi2 bar is a ramified character. Okay, we'll say a deformation rho of an ordinary and ramified residual representation rho bar to a coefficient lambda algebra A is an ordinary deformation if it's equivalent to a representation of that same form given above. So this kind of upper triangular matrix with an unramified guy on the diagonal and some other character on the diagonal as well. Okay, and these chi1 and chi2s, they're just characters on the Galois group G sub k sub lambda that we're working with. All right, so different perspectives on this setup. Proposition 29, let G be any profinite group and let I and G be any normal closed subgroup. So here G can be thought of as some Galois group maybe, and I is maybe our inertia subgroup at some prime. Let rho from G to GL2 of A be a representation, and the following three things are equivalent. Rho is equivalent to a representation of the form G maps to chi1 of G star 0 chi2 of G for characters chi1 and chi2 from G sub k sub lambda, or I guess this should just say G, to A cross, such that chi1 is trivial on I. In other words, think of chi1 as being unramified, and chi2 bar from G to k star is non-trivial on I. Okay. The equivalent to that is this other notion too. The representation A module V of rho equals V, so the representation space, admits an I-stable filtration 0 to V to the I to V to W to 0, which splits non-canonically as a sequence of A modules, where what is this V to the I? It's the A module of I invariant elements in V. It's the usual notation for invariance. Okay, and we want V to the I and W here, so these guys on the edges, to be free A modules of rank 1. Okay, so I think of those as like the representation spaces of these characters, essentially. Okay, they're like the eigenvalues. Well, the representation spaces of the eigen characters. Okay, and we also want to require one more thing if we want true equivalence. The I representation space W bar, which is W tensor to K, is not the trivial representation. Okay, that's just coming from the fact that our residual representation isn't trivial. Okay, so this is a very module theoretic interpretation of this very representation theoretic concept. And then 3, another kind of module theoretic perspective, both of those are equivalent to the fact that sub A module V to the I and V is free over A of rank 1. Okay, and the natural map V to I to V bar of I is surjective, where V bar equals V tensor to K, and the action of I on W bar, which is V bar mod V bar to the I, is non-trivial. So I think that's more or less just a rewording of 2 here. If you want to see the proof of this, you can see CSS page 304, although there's nothing particularly interesting there. Just helpful to have all those different perspectives. And if these conditions hold, we'll say that the representation rho is I ordinary, or if I is clear from context, as it will typically be for us, we'll just call it ordinary. Okay, I for us will just usually be some inertia group at some prime. And then I'll just make a remark. It follows from condition 2 of the 3 equivalent conditions that if rho is ordinary and V is V of rho, then no non-trivial A bracket I subquotient of the free rank 1 A module W, which is V mod V to the I, has a trivial I action. Okay, so what can we get out of this cohomologically? That's where we want to go next. Because if we have a deformation condition and then a residual representation that's absolutely irreducible, we can start talking about universal coefficient rings, and we can also start talking about tangent modules, which we know can be given cohomologically. So how does that look? Well, let's start here. So given an I ordinary representation rho from G to GL2 of A, we'll define n to V sub ord and n V to be the rank 2 free sub A module, A maps from V mod V to the I to V, contained in the full A maps from V to V, which is just n to V. Now, the action of G on V stabilizes V to the I, so the submodule n to V sub ord inside NV is certainly stabilized under the adjoint action of G on n AB. All right. So proposition 30, the homomorphism H1G end V ord to H1G end V induced by the natural inclusion of A bracket G modules is an injection. Thank goodness. Okay. So proof, CCSS page 305, not particularly interesting. So what we'll do is we'll say the I ordinary cohomology group H1 ord G end AV inside the full H1G end AV is going to go ahead and be the image of that injection above. And so what we have is that H1 ord G end AV is isomorphic to H1 ord G end of V ord. All right. So the big question is, do we have a deformation condition on our hands? Is ordinariness a deformation condition? And if so, what is H1 sub D, where D is the deformation condition? Proposition 31, fix a profinite group G in a closed normal subgroup I and G. If D is a class of I ordinary representations of G, then D is a deformation condition in the technical sense. Moreover, if rho from G to GL2 of A is ordinary, then the sub A module H1D G end AV inside the full H1 G end AV is given actually by the I ordinary cohomology submodule H1 ord G end AV, as expected, I think. So proof, you can see CSS page 306. Again, I don't think there's anything too interesting happening here. This is a pretty expected result. How about finite flatness? This is the last deformation condition we're going to need to consider. It's also the hardest one to deal with, and it leads naturally into chapter 13 of my notes coming up a little while from now. We have a whole chapter on this coming up. We're going to now consider the case that K sub lambda is the L-adic numbers where L is in 2. We'll let Q bar L denote a choice of algebraic closure of QL. We'll denote by G sub Q sub L the Galois group of Q sub L. If A is a coefficient lambda algebra and rho from GQL to GLN of A is a continuous representation, we'll say that rho is finite flat if for every Artinian quotient A naught of A, the induced representation rho naught from GQL to GLN of A naught has the property that its representation space V of rho naught, viewed as a finite abelian group with GQL action, is the QL Galois module that consists of the Q bar L rational points of some finite flat ZL group scheme. Okay, so we've already seen this definition before. Do we have a deformation condition? Yeah, this is non-trivial. This is the topic of Ramakrishna's thesis in chapter 13 of my notes. If D is the condition of being finite flat, then D does satisfy Ramakrishna's categorical conditions, and so it must be a deformation condition. Okay, so you can see Ramakrishna's thesis if you want to know more about that, or wait till chapter 13 of my notes. What's the cohomology group? This is a little bit harder to describe. We're going to use the fact that we can describe cohomology groups here in terms of extensions, because that's about the best we can do. We know by proposition 12 of this chapter that if A is Artinian and rho is finite flat, coming from a finite flat group scheme M over the L-adic integers, then H1 sub D of GQL and AB is nothing but extensions over spec CL of M by M, where V, the representation space of rho, is the GQL module M of Q bar L, and where this extension group here means extensions in the category, extensions of M by M in the category of finite flat group schemes over ZL. Okay. Now, in contrast with other local conditions we've encountered, the calculation of this extension group here is much more difficult, and it's actually only been carried out for our case of interest, which is n equals 2, but thank God it's been carried out at all, especially in the case we need, right? I'll end this video and hence this chapter, giving you some references for this finite flat stuff and looking ahead. So this calculation depends on the work found in Fontaine and Lafay's papers. So I'll end this chapter in this video by giving you some references here, so Fontaine's work, where you can go learn more about this finite flatness stuff and how this X group was calculated. We'll talk about this more though in chapter 13 of my notes. Okay, so that's the end of chapter 8. So it's an introduction to the theory of Galois deformations. And we sort of mined out of that all the results that we're going to need, minus calculations of the actual sizes of certain cohomology groups for the proof of Fermat's last theorem. So we're going to go on to chapter 9 next video next week. And there we'll look at the construction of the universal deformation ring. We haven't actually proven that it exists yet. We've just kind of acknowledged that it does, and we've looked at how Schlesinger's criterion might give us that. But we're going to go through a different, more explicit proof of the fact that it exists next chapter. So I'll see you then. Thanks for watching.